So the temperature at each level of the atmosphere, this object is able to adjust itself in such a way that you can fit this spectrum, and then what you're left with is kind of the plausible distribution of thermal structure or the plausible distribution of temperatures as a function of altitude in the atmosphere. And so one thing you can learn from this, obviously you're seeing absorption features, so you know the temperature profile is going to decrease with altitude or decrease with decreasing pressure, which is what you would expect to happen in an unirradiated object like a brown dwarf. And so usually you're left with these pretty obnoxious figures that kind of show the range, the distributions of parameter values for a given object, so you can sort of place a quantitative constraint on what the water abundance is and what its confidence interval might be, and then the degeneracies amongst the different species. And in some cases you can only place upper limits on the presence of, say, CO or CO2. But in this particular object, we're able to constrain the water abundance, the methane abundance, the ammonia abundance, and then the alkali metal opacities and things like that. So the Bayesian framework allows us to go from spectra to quantitative constraints on thermal structures and abundances of gases through radiative transfer. So we've done this for, this is kind of like schizophrenic here, but we've done this for a bunch of planets right now. A bunch of extrasolar planetary spectra, and we've kind of got a mixed bag of results.
Can I just ask how you explore this very complex parameter space? Is it really so straightforward? Markup, chain Monte Carlo?
Yeah.
Okay. Well, there's other ways to do it.
Yeah, there's other ways to do it. So, I mean, there's like sort of, if you go back to the early days, there's sort of simple Leavenworth Marquardt techniques, just basic curve fitting. There's Markup chain Monte Carlo. Now there's this fancy nested sampling that the cosmologists have invented decades ago, and they all more or less kind of do the same thing. They're going to give you a probability distribution on the properties of the atmosphere.
But the point is, you're confident that you fully exploit the parameter space.
Yeah, and the key thing is that you also try different methods to make sure, like this is just one method here.
Have you tried nested sampling?
Oh yeah. You get the same answers. Yes. Yeah. Oh yes, these are big issues. We know about them.
No, bit of a rhetorical discussion for the benefit of the audience.
Yeah, no, that's good. That's good. I can't say everyone's done that though. So you end up with kind of with a mixed bag of results, and so don't focus on any given individual thing, but you can measure the water abundances as a function of planet mass. So remember, one of the key questions we wanted to address was, how does the atmospheric metallicity change with planet mass? And we had this prediction from these planet formation models that the metallicity should increase as you decrease towards planet mass, unless you get into this regime. And here's just kind of a result from looking at applying one of these retrieval analyses on a bunch of planets where because we're kind of in this data-starved regime, the uncertainties on, say, the metallicity in the atmosphere are actually quite large, and so it's hard to have a conclusive result on whether or not the metallicity is decreasing. In this particular case, there's no trend. Maybe you could project this line with these data. But so this is just one example here. We can start to say something about the cloud top pressure, so effectively the degree of cloudiness in an atmosphere as a function of temperature. There's not really too much of a trend. Some objects have higher fidelity data than others, so we can get higher precision constraints. We can begin to address the nature of the thermal structures in these atmospheres. Maybe we can start to say something about the degree of disequilibrium or chemical equilibrium in these planetary atmospheres. But kind of the take home from looking all of this, I mean, these uncertainties, it's kind of hard to read here on the screen, but these uncertainties are spanning many orders of magnitude in terms of, say, measuring the water abundance in these atmospheres. And the temperature uncertainties are also several hundreds of Kelvin. And then where a cloud might be in an atmosphere, at what altitudes it begins to matter, or what pressure levels a cloud starts to matter, also spans many orders of magnitude. And so we're kind of...
How do you tell the difference between haze and no atmosphere at all?
Ask Laura Kreiber.
No, because in both cases you have featureless.
Yeah, so...
These are gas giants.
Yeah, these are all gas giants, yeah, so, right.
Okay.
Sorry, I should specify, yeah.
Okay.
So if we're in a terrestrial planet regime, certainly that's going to be a challenging issue, and you would have to maybe look at other wavelengths where you would expect, say, hazes not to matter. So if you were to try and look at blow-off, for instance, if you were to look at a UV line and look at the upper atmosphere, If you didn't see a line there and you had a flat transmission spectrum in the infrared, then maybe you would say that the atmosphere is airless.
So you can't tell the difference.
Yeah, in that case. But yeah, these are all gas giants. And I should also mention, I'm kind of like blowing through this, but I should also mention that most of the spectra that we see, they're not flat lines with wavelength. They have features in them, but those features are squished relative to what we would expect for a pristine, clear atmosphere. And we think that that squishness, that reduction in feature size, is due to the fact that we have a really opaque absorber, which we've been calling a cloud, prevent those rays of light from passing through the limbs of the planet, right? So you might not see, you could see muted features in the transmission spectra due to this effect, but if you were to, say, look at the thermal emission from the planet, if you were to look at another location on the planet, say the day side as opposed to the evening and night terminators of the planet, plus your geometry is different, you might see features in that case. And so you kind of want to look at the two together.
And then so if you have a flat spectrum, how can you get a bound on the lowest pressure for the clouds? Couldn't they put the clouds at arbitrarily low pressures, high altitudes? So yeah. Why not present a one-sided constraint? Like, why you have error bars here, but I could put a cloud at even lower pressures.
Oh, I didn't do this. This was no.
Why not?
Yeah. So actually, these.
Why not just present a one-sided?
Yes. Well, these error bars are misleading right here. So I would say that these are all just upper limits. Sorry, lower limits on where the cloud can be.
Yes, but if you integrate from one side, you actually have a more interesting constraint. You see what I'm saying? You're sticking.
Yeah. No. I agree. Yeah. So if for any given object, you would say, so say for this object, effectively, if you were to look at the, if you were to actually look at what the, say, Markov chain Monte Carlo produces, right, it would be sort of a step function in the probability of cloud location as a function of pressure in the atmosphere. So all of these right here, they didn't do this in this figure right here, but all of these should be upper limits on here. So I agree with you, because that tells you something interesting. You're saying that the cloud in the clouds in these situations, because we see features,
has to be at least.
That has to be, well, it can't be higher than this altitude. It has to be at this altitude or lower, because if it were higher, our features would be more muted.
Aren't some of these flat?
No, none of these here are flat.
Those won't.
None of these here are flat.
But Mike, I mean, this is you basically have a degeneracy between the base of the pressure, the T0, and the composition profile of the molecule, right? So how do you handle that?
This is one of my favorite discussion topics. I could go on for hours about it.
Oh, I can be the opposite.
We will talk about it later. I have opinions. That degeneracy is not an issue because you have opacity sources on either side that can break that degeneracy.
So that figure at the top, which is a little shocking to me. So
this is a version of this figure. There are different versions of this figure that show a trend.
No, but actually, so are those data all analyzed using the same reference pressure?
No, the reference pressure is a free parameter in these models.
Oh, okay.
Yeah, we'll talk about it.
Someone's going to have to go back to that and do it all like, anyway, so.
These are good questions, and the reason why I wanted to show you all this is because this is the problem, right? So there are a lot of things we want to know, and as you guys are correctly calling me out on the BS, because we have these large uncertainties, we're dealing with a limited wavelength range, right? We're dealing with a limited wavelength range. We're dealing with limited signal to noise. And there's a bajillion things we want to know about the atmosphere. So there's going to be many inherent degeneracies that result in these large uncertainties on the stuff we want to know, like cloud properties, abundances, temperatures, disequilibrium chemistry. So we're still in this regime where, in a sense, you get out what you put in. So you kind of bias your result in a way depending on kind of the parameterization you put into your model to begin with. So I would say, given the data we have now, we're still kind of in this model slash, in Bayesian speak, prior-driven regime. And I apologize, Laura, you've seen this like 55 times already. But this is sort of my philosophical existential crisis in the exo-atmosphere community in sort of janky math notation, where we have all this physics that we want to know, we don't even know what all the physics we want to know is, so that's kind of a problem. But then we have these observations, and we want to kind of figure out which observations are sensitive to which physics. You know, if I want to know this physics 1 right here, what set of observations should I obtain that help me, that give me my biggest bang for my buck, so to speak, right? Okay, and then for any given observation, this is where the degeneracy comes in, there's a boatload of physics that can control those observations. And so, you know, there's all sorts of off-diagonal terms here. That's what makes this problem really hard. And so the idea is that we'd want to invert this, and then we'd be happy, we'd have our abundances, temperatures, we could answer all these questions about habitability, you know, there's clouds, all this stuff. Okay? And it's because we're kind of in this ill-posed problem.
Why aren't you calling that Jacobian matrix?
It is a Jacobian matrix. Okay. Yeah. In classic atmospheric retrieval speak, I would call this a Jacobian. This is my philosophical version of it. And so the problem is, you know, we have m available planetary photons, or pieces of information that are real, and there are n unknowns that are approaching infinity. So the number of physics n is bigger than the observations we have right now. So that's why we have these issues. We have these degeneracies. We get results that you guys see in the literature where a paper will come out making some claim, and then 3 days later another paper will come out saying, no, that's crazy. It's because we're in this regime. And so we're still very much in this assumption-driven regime. I know that sounds doom and gloom. But behold the future, maybe. JWST will solve some of these issues, right? So James Webb is going to be about a factor of 10 or more in resolution. The mirror is bigger, which doesn't buy you that much more signal to noise. It's linear in the mirror diameter.